Welcome to Black Hole Basics, where we explore the deepest mysteries of the cosmos and unveil the secrets of gravity. In April 2019, humanity saw the unseeable, the very first direct image of a black hole's event horizon. This glowing orange ring captivated the world, proving that these theoretical monsters of gravity actually exist in our physical reality. For decades, black holes were merely mathematical predictions, existing only in the complex equations of Albert Einstein's general relativity theory. Einstein predicted that if enough mass is packed into a small space, spacetime curves infinitely, trapping everything, even light. We call this region a black hole, a point of no return where the gravitational pull is simply too strong. To find this monster, scientists look toward Messier 87, a supergiant elliptical galaxy 55 million light-years away from Earth. At its center lies a black hole 6.5 billion times more massive than our Sun, a true giant. Photographing it was like trying to take a picture of an orange on the surface of the Moon from Earth. No single telescope on our planet is large enough or powerful enough to capture such a tiny detail in the sky. To solve this, scientists created the Event Horizon Telescope, a global network of 8 radio telescopes working in perfect unison. From the frozen ice sheets of Antarctica to the high deserts of Chile, these telescopes span the entire globe effectively. By synchronizing them, they created a virtual telescope the size of Earth itself, achieving the necessary resolution to see M87. Synchronization was critical, requiring atomic clocks so precise they would only lose 1 second every 100 million years. They used a technique called very long baseline interferometry to combine the signals received at different locations into one stream. The team observed the target for several days in April 2017, praying for clear skies at all sites. Miraculously, the weather cooperated globally, allowing the telescopes to record the faint radio waves emitted by the black hole's surroundings. The amount of data collected was so massive that it could not be transmitted over the internet to the researchers. Instead, hundreds of pounds of hard drives were physically flown to supercomputers in Germany and the United States for processing. They even had to wait months for the Antarctic winter to end before planes could fly out the final data. Once gathered, supercomputers known as correlators synchronize the playback of the data, aligning the signals to within a fraction of a second. Computer scientists developed new algorithms to reconstruct an image from the sparse data, filling in the gaps of the puzzle. Because the telescopes didn't cover the entire Earth, the data was incomplete, requiring smart mathematics to predict the missing parts. To ensure accuracy, 4 separate teams worked independently with different algorithms to see if they would produce the same image. When they finally compared their results, every team had produced the same ring structure, confirming the image was scientifically valid. The resulting image shows a bright ring of emission surrounding a dark central region, exactly as Einstein's theory had predicted. The dark center is not the black hole itself, but its shadow, cast against the bright background of hot gas. This shadow is caused by gravitational lensing and the capture of light by the event horizon, the point of no return. The bright ring is light from hot gas swirling around the black hole, bent by gravity toward our line of sight. This matter forms an accretion disk, heating up to billions of degrees as it spirals inward at nearly light speed. You might notice the ring is brighter on one side. This is due to an effect called relativistic Doppler beaming. Matter moving toward Earth appears brighter and more energetic, while matter moving away from us appears dimmer and redder. This asymmetry tells us that the gas is rotating and gives us clues about the orientation of the black hole's spin. The match between the theoretical simulations and the actual image was a triumph for physics, confirming our understanding of gravity. It was a moment that Stephen Hawking would have loved, seeing his theoretical work validated by hard observational evidence from space. But M87 was not the only target. The team also aimed their telescopes at the center of our own Milky Way. There lies Sagittarius, a star, a black hole 4 million times the mass of the Sun, much closer to home. Although closer, Sagittarius, a star, is 1,000 times smaller than M87, making it incredibly difficult to get a clear picture. Gas orbits M87 in weeks, but it circles our small black hole in mere minutes, changing appearance while being photographed. Imaging it was like trying to take a sharp photo of a toddler running frantically around a room with the shutter open. It took 3 extra years of data processing, but in 2022, we finally saw the heart of our galaxy. Despite the difference in size and environment, both black holes look remarkably similar, confirming that gravity acts consistently across the universe. Scientists later analyzed the polarization of light from M87, revealing the twisted magnetic fields that surround the event horizon edge. These magnetic fields act like gatekeepers, launching powerful jets of particles outward that span thousands of light years into the galaxy. This connection helps us understand how black holes can influence the evolution of entire galaxies, shaping the cosmos we see. The work is far from over. The Event Horizon Telescope team is currently upgrading their network to capture even sharper images. They are adding new telescopes in Greenland and Africa, which will improve the image quality and allow for color fidelity. The next goal is not just a still photo, but a full video, showing the dynamic flow of matter in real time. Future missions may even place radio telescopes in space, creating an array larger than Earth for unprecedented detail and zoom. Every major galaxy likely harbors a supermassive black hole, meaning there are billions of these monsters waiting to be studied. These images are testing the limits of physics, looking for cracks in Einstein's theory that might reveal a deeper truth. Could black holes be portals? While unlikely, studying the event horizon is our only way to probe the nature of gravity. What we are really seeing in this image is light fighting against the strongest force in the universe, and barely escaping. The gravity is so intense that it acts like a lens, bending light from behind the black hole into our view. This image reminds us of our place in the universe, small observers capable of understanding the most colossal forces of nature. It inspires a new generation of astronomers and physicists to ask new questions and develop technologies we cannot yet imagine. Perhaps one day, humanity will not just look at these images, but travel to the stars to see them firsthand. From a scribbled equation on a chalkboard to a global effort involving hundreds of minds, the journey was truly incredible. The resolution achieved is equivalent to being able to read a newspaper in New York from a cafe sidewalk in Paris. The hard drives containing the data are now historical artifacts, holding the weight of the first visual proof of the abyss. Black holes also challenge quantum mechanics, creating the information paradox, which asks if information is destroyed when it falls inside. Solving the mystery of black holes might finally unite gravity and quantum mechanics into a single theory of everything. As technology advances, the blurry orange donut will resolve into sharp filaments, revealing the turbulent dynamics of the accretion flow. Space telescopes like James Webb are also studying the environments of black holes, adding infrared data to the radio pictures. We use radio waves because they can pass through the thick dust clouds of galaxies that block visible light from us. Visible light gets trapped by dust, but radio waves travel unimpeded for millions of years to reach our sensitive detectors. Interferometry is the magic that allows us to combine these waves, using the interference patterns to calculate the image structure. As Earth rotates, the telescopes change their viewing angle, filling in more data points and improving the final image quality. The mathematics involved relies heavily on Fourier transforms, converting raw frequency data into the spatial map we see as a picture. While some names became famous, the collaboration involved over 200 researchers from institutes all around the world working together. Institutions like MIT, Max Planck, and the European Southern Observatory provided the funding and expertise to make this dream possible. Hollywood got it surprisingly right in the movie Interstellar, thanks to scientific consulting, but the real thing is even more profound. M87 has a thick, donut-shaped disk, while other black holes might have thin, razor-sharp disks depending on their feeding habits. Black holes are not vacuum cleaners. They only consume matter that wanders too close to the unstable orbit of the edge. If our sun were replaced by a black hole of the same mass, Earth would keep orbiting safely without getting sucked in. Near the event horizon, time itself slows down significantly relative to the outside universe, a phenomenon known as time dilation. To a distant observer, an object falling in would appear to freeze and fade at the edge, never truly crossing over. But for the traveler, they would cross the horizon without noticing anything special, until gravity eventually ripped them apart. At the center lies the singularity, a point where density becomes infinite and our current understanding of physics completely breaks down. It is here that we need a theory of quantum gravity to explain what truly happens to the matter that enters. Most black holes spin, creating a region called the ergosphere, where space itself is dragged around at impossible speeds. Theoretically, a sufficiently advanced civilization could extract energy from this rotation, using the black hole as a massive power source. For now, we simply marvel at the image, a glowing ring that connects our small minds to the vast cosmos. Since the release, thousands of scientific papers have been written analyzing every pixel of data to learn more about gravity. The universe is filled with diverse wonders, but the black hole remains the ultimate test of our intellect and imagination. It reminds us that there is still so much left to discover, waiting for curious minds to look up and wonder. Future projects like the Next Generation ET will allow us to see the photon ring in even greater, sharper detail. We may soon image black holes from the early universe, understanding how they formed so quickly after the Big Bang. We are learning that black holes are not just destroyers, they are architects that help shape the structure of galaxies. While violent and destructive, these cosmic giants are far away, posing no threat to our beautiful and fragile blue planet. The first image of a black hole is a testament to human ingenuity, global cooperation, and our unyielding desire to know. We have stared into the abyss, and for the first time in history, the abyss has finally stared back at us. This is not a dead static object. It is a breathing engine of energy, powering the galaxies surrounding it for eons. It took 2 years of silence and hard work before the team was ready to show the world what they found. That moment in April 2019 will be remembered as a pivotal point in the history of science and astronomy. Studying these objects might even help us build better quantum computers, using the principles of information scrambling found in nature. As the universe expands and stars die out, black holes will be the last survivors in the far distant future. Trillions of years from now, the universe will be dark, populated only by these silent giants slowly evaporating via Hawking radiation. Stephen Hawking predicted that black holes eventually fade away, leaking energy back into the universe until they explode and vanish. But that is a story for the very distant future. For now, they are the most powerful engines in existence. The image of M87 star stands as a beacon of human achievement, a victory of curiosity over the impossible darkness. So the next time you look up at the night sky, remember that the invisible is just waiting to be seen. It took a telescope the size of the world to see it, proving that we achieve more when we work together. If you enjoyed this deep dive into the first black hole image, please consider subscribing to support our science content. Check out our other videos where we break down general relativity and quantum mechanics in simple terms for everyone to understand. We want to thank the Event Horizon Telescope collaboration for making their data and research accessible to the public and creators. The universe is a vast and mysterious place, and we are just getting started on our journey to understand it all. What cosmic mystery should we explore next? Leave your thoughts in the comments below. We love reading your interesting suggestions. You have been watching Black Hole Basics, your guide to understanding the complex universe in the simplest way possible. Thank you for joining us on this journey across space and time. Keep looking up, and keep wondering about the stars. See you in the next video. Until then, stay curious and keep exploring the wonders of our amazing universe. This has been a production of Black Hole Basics. Goodbye for now, and thank you for watching.